Welcome back. I hope you had a good weekend. I did. I was preparing today's lecture. No, that's not true. I was preparing Wednesday's lecture. Okay, so we're going to change pace for this week. Things are going to be somewhat different to what we were doing last week and the week before. We're going to be looking at quantum theory kind of from a more general structural perspective. So quantum theory can be divided into two distinct components. The first one is to do with identifying the level structure of some particular physical system. And the second one is to do with how an agent interacts with different components and then makes predictions about statistics that they would expect to see in an experiment. So I'll elaborate on that a little bit. So in the first one, I said it's identifying the level structure associated with a physical system. And the second one is to do with predicting the statistic. Associated with an agent's interactions with the system. So in the first category, we would have things like which Hilbert space is appropriate to describe a particular physical system. So what is the Hilbert space? And related to that would be what is an appropriate vector to describe, or appropriate state to describe the actual state of that physical system. Also, in that category, you would have what are the physical forces affecting the quantum system, which would lead to the Hamiltonian describing that system. And also, which operator or observable represents a particular experimental measurement procedure. So these are all specifics to do with a particular system. And then here, we can have, so given a certain preparation, of a system, and a certain transformation, what is the probability of getting a certain outcome? So you can think of this component as kind of asking, how do all of these things fit together? This is describing a specific system, and this is saying, given that you have this specific system, how do you put everything together to predict the statistics of an experiment? And so both of these components are necessary to describe a specific experiment or some sort of phenomena. But you can actually just work with this component without worrying about the details of the actual, the specific system that you're interested in. And so what we're going to do for most of this week is to just focus on this component. We're going to assume that a system can be described in some way, and then we're not really going to worry about it. And we're just going to look at the formal structure of the theory. Does that make sense so far? Okay. And so this component is actually, it's really natural to talk about it in terms of something called the operational framework. And so I want to motivate the operational framework a little bit before we go on. So you saw a little bit about the operational approach in Rob's talk at the beginning, where he was talking about having certain preparations and certain measurements. And typically what we do is we split up the theory into 3 separate objects. So the first object is a preparation device. So you can think of it as a box that has a particular output that maybe you can think about something coming out of it, maybe not. And so this preparation device, it's going to have a knob that you can use to fix the settings of your preparation. And it's going to have a little button that you can press to say, okay, make my preparation. And we're going to assume that this preparation can be repeatable. So every time you pick one particular set of settings and press the button, it's going to be the same preparation. Then the second box is called the transformation box. And it has an input and an output. And also it has some settings that you can, it's got a little knob, you can turn it to maybe specify the particular transformation you're interested in doing. And then the final box is the measurement box. So the measurement box has some input. It has a knob that you can turn to choose the measurement settings, but it also has an output. So it has some sort of dial that then tells you what the measurement results were. So it seems kind of strange talking about quantum theory in this way. And so I want to spend a little bit of time motivating why people think about it this way. And to do that, I have to talk a little bit about the issues associated with interpretations of quantum theory. So this is definitely not a course about interpretations. And if you're interested in that, you can take the Quantum Foundations course, which will be offered in January. But in some sense, it's difficult to talk about quantum theory without it kind of talking about the interpretational issues. So I want to spend some time doing that. Okay, so what are these interpretational issues? Well, they're associated with whether you think about psi, or maybe let's forget psi. Whether you think about psi as representing the physical state of the system, or whether you think about it representing your state of knowledge about the system. So, or maybe a little bit of both. And so if you've never asked yourself the question, what do I think the state psi represents? then probably by default you're a realist. So a realist is someone that thinks the state psi represents the state of the physical system. So, I mean, being a realist, it's a pretty reasonable thing to do, right? Like if I have some sort of wave function representing some sort of, let's say it's a localized wave function like this, and I evolve it according to a unitary, and maybe, it's like moves around or whatever, it's pretty natural to think about this wave packet as corresponding to, a physical particle that's moving around the same way that my quantum state, my mathematical object, is moving around. And typically the other theories that we have also make this connection between the mathematical objects and the physical systems that we're dealing with. So it seems natural to start thinking about psi this way. But problems arise once the wave function kind of becomes delocalized. So one example of this is, let's say I have a double slit, and in comes my wave packet. And then, well, what happens afterwards? Well, mathematically, it kind of splits into a superposition of these two wave packets. And then if we model what's going on, or even experimentally, we would find that we get some sort of, interference, fringes on some screen. But if you now think about this wave packet as corresponding to some physical particle, it's kind of strange because, what's happening is the particle going through both slits at the same time. Is it interfering with itself? I mean, mathematically, we see what's going on, but physically, it's like really strange. What does it mean for a particle to interfere with itself? What does it mean for it to go through two slits at the same time? It's kind of strange. Another strange thing is, like, if you go back to the example we were looking at before of having an excited atom, and let's say we wait some time and this atom decays, and it, let's say it's not in a cavity, but it's just, somewhere in space. It decays, it spits out a photon. Then this photon, the wave packet for this photon is just going off in all directions. After some time, a long, long, long time, this wave packet's going to be like, I don't know, could be covering the entire universe. And then if somebody now detects that photon, then instantly it's going to collapse this, wave function like everywhere. So the wave function on the other side of the universe is going to instantly be affected by the detection of the photon on that, this side of the universe. And so if you think about this wave function as physically representing the particle, then this like very non-local thing is happening. So it's kind of unsettling. So if you don't like this idea of non-locality, what are your other options? Well, maybe rather than thinking about the state as being corresponding to the physical state of the system, you might think of the quantum state as being something like a probability distribution. So this doesn't seem so strange. We kind of have things like that classically. So okay, maybe I'll. Okay. And the cool thing about thinking about the wave function as being something kind of like a probability distribution is that it makes this collapse not mysterious at all. And so I want to kind of give you a classical analogy that would emphasize why wave function collapse is not mysterious when you think about things this way. So imagine, so classically, if you have just a single particle and you want to see how it evolves, then you could, use Newton's laws to track the evolution. But let's say at first you don't really have precise knowledge about the state of this particle. So just classically, you could describe the state of the particle as being some sort of probability distribution over position and momentum. And you can actually model the evolution of that probability distribution using the Liouville equation. So that's an equation of motion for probability density functions. So you could, model this evolution for some time, and maybe after some time, your description of the state of the system, it's going to be some other probability distribution that looks like this. And then let's say you want to make a measurement, and maybe you're going to be measuring the position of this particle, and maybe your measurement is it's not fully precise, but it's got some sort of resolution that's smaller than this description of your state. And so let's say you get an outcome saying that your particle is now within this little region of position. So then you're going to update your probability distribution to now be this. And you can kind of say, well, now I've collapsed my probability distribution of this particle, and this is my updated distribution. And that's not very mysterious at all. I mean, in this case, you can say, well, the particle was really always somewhere in here, but it was just my knowledge of the system that described it like this. So that seems really nice, but it's also problematic because if you were to, classically it's fine, but quantum mechanically, if you were to make this analogy between the quantum state of the particle and this probability distribution, you would have to ask the question, well, if it's a probability distribution, what is the distribution? The distribution has to be over something. And what is that something? Well, that something would have to be some sort of thing outside of the theory, outside of quantum theory. It'd have to be some sort of maybe hidden variable. And so one of the things that Bell's theorem told us, the Bell experiments that were done just recently, they ruled out the existence of any local hidden variable theory. And so that means that if you want to think about the state as a distribution over some sort of hidden variable, you have to accept that it's going to be a non-local hidden variable. So you kind of can't escape this idea of non-locality. You either, if you think about the wave function as being real, then you get non-locality. If you think about there being some sort of hidden variable, it has to be non-local. So both things are kind of unsettling. And different people, some people really don't care. Some people feel really strongly about one or the other. And you might think that if you have different people having these really opposing ideas, maybe they can never, communicate. Maybe they can never make progress. But there is a way that there are some things that realists and people who think about the state as a probability distribution, there are some things that they can agree on. And so these things are as follows. So they can agree that, I can make some type of experiment, right? I can go through some sort of preparation procedure, and I can go through some sort of measurement procedure. And they can see what happens if I, prepare some type of state and measure some other state. And they could, repeat this process over and over again, and maybe keep changing the settings of the measurement device until they get to a point where every time they press, play, they get a click that registers exactly the same output. So when they do that, once they know that, I press play here, I get exactly the same click here, they can say, well, there's some sort of connection between what's going on here and what's going on there. And maybe I can assign some mathematical object to this procedure that I've described here. So maybe they can say, well, this corresponds to the state psi. And then they can assign that in state psi. And then maybe they can keep playing around with the settings, keep doing the same thing here, but play around with the measurement settings until they never get a click. And so then they can say, well, I can associate something orthogonal to psi there. And then they can, kind of keep repeating this procedure and make up, kind of create mathematical objects that predict the statistics of what's going on here. Every time I press some button here, I get some click here, and so on. And from that, they can build this operational theory of quantum mechanics. And so this is something that is nice because it leaves you agnostic about what the interpretational issues are. You don't have to worry about what the wave function actually represents. All you're talking about is, what am I doing in the lab and what are the statistics that I get out as a result of doing those things. So that's good, but there are some unsettling things about the operational framework as well. And that is that, all the other theories that we have, the other theories of physics, they're kind of about what's happening in the universe independent of what we're doing. While here we have a theory of physics that really depends on us going in and, doing something in the lab. So it's also problematic. And what researchers typically do is they kind of switch between, thinking about things operationally, thinking about things as a realist, thinking about things in terms of the states being probability distributions. And so if you're going to be continuing on in fields related to this, it's important for you to kind of be comfortable thinking about things in terms of all of these different pictures. And so what I was saying earlier was that if you're interested in more of the interpretational issues, you should take the Quantum Foundations course. But even if you're not interested in the interpretational issues at all, you should definitely still try and get a good handle on the formalism that I'll be talking about here, because it's the modern formalism that researchers are using now to study quantum systems. So if you're doing any research related to quantum theory, a lot of the time people are going to be using this generalized framework that I'll be talking about here, regardless of whether they care about interpretational issues or not. And a lot of the things I'll talk about here in terms of entanglement and reduced states, that's going to be useful also in kind of crossovers with other disciplines. So, outside of research directly related to quantum theory, people are, thinking about things like Hawking radiation, or maybe like entangled pairs being created at the edge of the event horizon, or cosmologists are starting to think about descriptions of the light in the universe in terms of, the quantum state of the light. So in all of those areas, having a good idea of how to use this operational framework will become really useful. So that's my pitch for, for getting comfortable with it. Okay, so I already introduced the three objects that are the key players in this operational approach. And typically, the way that the framework is presented is in terms of postulates. So there will be three postulates that are each one of them corresponding to each of these objects. There'll be the preparation, the transformation, and the measurement. And what I'm going to do this week is to kind of start off with the simplest case and then build things up in terms of complexity. So today, I will just start off with talking about the realistic postulates. The ideal postulates, which will be very closely related to things that you've already seen. And then at the end of the lecture, I want to introduce something called the block sphere and quantum state tomography. So both of those things are really nice because they'll give you kind of some conceptual tools to try and get a handle on what these things are if you're not going to be thinking about them from a realist perspective. So that'll be today. And the block sphere will become important because I'm going to use it throughout the week to kind of help you build intuition for what's going on. Then tomorrow, I will extend the postulates to incorporate statistical mixtures. So we will have statistical mixtures of the ideal operations, and that'll give us a more general framework. Then on Wednesday, I'll talk about what happens when we've got more than one system and what happens when you have entanglement between those systems. And that'll set us up to talking about the even more general version of the realistic postulates, where we talk about the descriptions on a particular system as a kind of effective description of a much larger ideal system. And so that becomes interesting when those systems are entangled. And then, yeah, at the end, I'll go through the quantum teleportation protocol, just because it's fun and maybe it'll get you a bit interested in the quantum information course. Okay, so any questions so far? No one's like concerned? Who, okay, maybe let's have a vote. How many of you would consider yourself realist? Well, yeah, that's the right answer. Okay, how many of you would consider yourselves people who think of the wave function as being a probability distribution over some hidden variable? Yeah, okay. That's probably half up. So what do the rest of you think? Superposition of both, fantastic. So who's undecided? Okay. Yeah. Okay, so, I have a disclaimer. Everything I'm going to do this week is going to be for discrete systems. There are some subtleties involved. So everything I will do can be extended to continuous dimensional systems. I will not be doing that at all. If that is something you're really interested in, you could go back and look at Joseph Emerson's lectures. So in the past, he has given a full 3-week course on the operational framework, and there he really goes into the nitty-gritty details of continuous dimensional systems. I won't do that here. Okay. All right. So let's start. Ideal postulate. Okay, the first postulate is the preparation postulate. And it says that an ideal preparation is described by a Hilbert space vector psi. So in order to try and remain agnostic about how we should interpret what psi is, I'm going to try really hard to use the term ket rather than state whenever I refer to it. So the ket is the mathematical object as opposed to the physical state of the system. Sometimes I will slip up just because it's natural to slip into thinking like a realist, but I just want to get the terminology straight. Okay, so at the beginning of the course, you guys already discussed all of the properties of Hilbert spaces, so I'm not going to go into that here. I just want to give you a few reminders. So there's something called the dual space to the Hilbert space, and it consists of all continuous linear functionals mapping elements of the Hilbert space to complex scalars. And due to Ries's theorem, in Dirac notation, we have this nice correspondence between the dual space and the Hilbert space. So in Dirac notation, this bra refers to a unique element of the dual space. And the other thing I want to remind you of is that so all vectors that differ by scalar multiplication with an arbitrary phase, so anything e to the I phi multiplied by the cat, they are physically indistinguishable. So sometimes it's more natural to then think about this object called the density operator, which is just the outer product of the cat. So in quantum theory, any ket can be expressed as a discrete linear combination of orthonormal elements. And we also have a condition that's called the normalization condition. So given that condition, what would the constraints be on this complex number Cj? Yep. So sum over j all squared should be 1. Okay, so even though what I said is that we can think about the second component of quantum theory independent of what the physical system is, I think it's nice to look at some examples of physical systems just to try and get our, get some intuition about what the math is telling us. So I thought maybe you guys can volunteer some examples of physical systems that we've already encountered, or of states of physical systems that we've encountered that have been represented in orthonormal bases. Coherent state? Yeah. And what was the basis that they were represented in? Yeah. So I won't write down what the coefficients were, but yeah, we had coherent state. Did we see anything else? Okay, three states. Yeah, okay, so lots of states of light written in the number basis. I guess I won't write them down. Have we seen any any non-states of light? I don't actually know if you guys have. But... Yeah, spin half states. Okay. Okay, we could have something like C up, so spin up plus spin down. That's a nice coherent superposition. Okay, cool. So, I mean, there's not too much to say about the ideal postulates, so we're going to go through them pretty quickly, although measurement gets a little bit interesting. But okay, let's now move on to transformations. Okay, so after a preparation is made, then and before a detection happens, we can describe what's happening in terms of a dynamical transformation. So the second postulate which will also not be surprising to you, is that ideal transformations are generated by a linear operator U satisfying something like the Schrödinger equation, but for the operator. Okay, I'll bring this up in a second so you guys can see. Where here H is a self-adjoint operator representing the energy okay, well, T is time. I'm not going to write that down. And it's subject to the condition that the operator at T1 is equal to the identity. So I think you guys are pretty familiar with how the unitary evolutions go. So I'm not going to say so much about it, but we'll go into a lot more detail of transformations once we look at the generalized system. Okay. Oh, and okay, maybe one thing I want to say is that the form of H is not going to be part of the postulates. So that's something that fits into this first component of identifying what the system is. Here, we're just going to take H to satisfy, well, actually, no, we're not going to say anything about H. Okay, so then the third postulate is to do with measurement. and that is that an ideal measurement is represented by a collection of projection operators. So the collection is this set of operators Pm, and then the index M refers to the measurement outcomes that may occur in the experiment, and the probability of finding M given the preparation psi is given by this expression. So this thing here is known as Born's rule. Okay, and so what this does is it predicts the relative frequency with which you're going to get each of the outcomes M. So for example, let's say you made the same preparation over and over and over and over again, and then made a measurement corresponding to this set of projectors. And every time you made the measurement, you got some outcome M. You then put a little well, you added something to your histogram. So over time, as you're collecting more and more and more statistics, you would get different heights of your histogram. And this would give you some information about the preparation that you had made. So this is actually a more detailed description of measurement than thinking about expectation values of observables. So the expectation value would really just give you the mean of this distribution, but here we're describing our more detailed measurement. And so it's kind of, you know, historical why originally people were thinking about expectation values. And I think it's to do with what was available technologically. So originally, a lot of the quantum experiments were, you know, done on collections of systems. So you would have maybe like, I know, a bunch of spins, and you would apply some sort of magnetic field to it and only extract some average value of some observable. Or maybe you had like a state of light that had a lot of photons in it, and you'd just be able to measure, you know, the average polarization or something. But then as experiments got better and better technologically, we were able to access, you know, individual quantum systems, and we were able to build up statistics by, you know, measuring systems one by one. And then it became necessary to then have this more kind of fine-grained theory of measurement. Okay, but we can actually make a connection between this and measuring the expectation value. So let's say I have some operator. Okay. So consider an observable described by the operator A. So A can always be decomposed into what's known as a spectral decomposition. Which I don't think you guys can really see. So these are going to be the eigenstates of the operator, and these are the eigenvalues of the operator. And now if I just write down the definition of AM now, if I write down the definition of what an expectation value is, well, it's going to be the value that I'm interested in times the probability of getting that outcome. So, well, it'll be a sum over all of the values where each one is weighted by the probability of getting that outcome. So we'll have sum over AL times the probability of getting L. And then we know that that's given by Born's rule. And then using the spectral decomposition, I can rewrite this as which would be the expression that you've seen before for computing the expectation value given some particular state psi. So you can see that it, connects with what we actually know as the definition of an expectation value in terms of probabilities of outcomes. Okay, so far we've only talked about measurement in terms of predicting the statistics, but we can also say something about how to describe the ket after we've gotten a particular outcome. So this is given by what's called the state update rule. So give an outcome M, the system after measurement is going to be, we can label it with the subscript M, and it'll be the projector acted on the state, on the ket describing the system just before the measurement, and then divided by the square root of the probability of getting M. And these projection operators, they satisfy this property that PL PK is equal to delta function over K and L I don't know if that's the right way to do it. Well, anyway, what I mean by this is that if the projectors are the same, then they satisfy this property called idempotence, which means that they multiply to itself. And if they're different, then the overlap between them is 0. Yeah. Should I, sorry? That one? Yeah. Yeah, I think I've just written it down wrong. Maybe I just want to write it like, well, I don't know how I want to write it. How would I write what I'm trying to say in words? I had it written down and then I'm like, this does not look right. Maybe I just want to say that. That's what, you know what I mean. Okay, so I'm going to ask you to answer some things for me. So given that description, you're going to tell me, I'm going to write some things down and you're going to tell me whether you think it's a projector or not. Start with an easy one. Hands up if it's a projector. Hands up if it's not a projector. Yeah, I'll start with that question first. Okay, so most people say yes, that's a projector. Okay, what about Is that not a projector? Okay. I mean, that's not even an operator, right? Like it's okay. So no. Okay, what about that? I'm just going to get you to yell out. People are shaking their heads. It's not a projector. Why is it not a projector? Yeah. Okay. What about, oh, I'll write it here. That. I see one person who is moving their head. Another person moving their head. Well, no. Well, where these two, so, okay. They are all, yeah, sorry. Okay, so yeah, that's a projector. Because if I square it with itself, I will get itself out. Very good. Okay, so the last thing I wanted to say about measurement. So this is what I've found. The one thing that students who haven't seen this stuff before, they kind of use the language that they used when talking about expectation values. They kind of map it in a way that seems natural to talking about projective measurements, but it doesn't quite work. So what I mean by that is when we talk about expectation values, we say something like, let's measure an observable A. And then kind of the result or the outcome of that measurement is, say, so people say the result is the expectation value, which is 0.5. When we're talking about projective measurements, when we say that we're measuring an observable A, what we really mean is that we're measuring in a basis corresponding to the eigenstates. Okay, so sometimes you'll say, so I'll be talking about block spheres a lot, so I'll be using the Pauli operators, and people will say things like, oh, measure in this sigma z basis. What they really mean is not measure the expectation value of sigma z, they mean measure in a basis corresponding to the projectors 0 and 1. But then in terms of what the results are, we don't say that then the result is the probability of getting a particular outcome. We say that the result is, okay, well, the outcome is, okay, it's not the probability of getting n. Okay, the outcome is m. So that might kind of seem strange, but I see a lot of students using the terminology saying that people say things like, what's the way that they, okay, they say, I measure, right, okay. So they say, yeah, people say, I measure the projector P0. Okay. You never measure a projector. You measure something that's a set of projectors, and a specific value of m is an outcome. So maybe we'll come back to that, but I just wanted to make a note on that. So you measure in a basis, and you get outcomes corresponding to individual m's. Okay, so like I said, all of the discussion for this week, it's going to be in terms of finite dimensional systems, but they're going to be d-dimensional systems. So everything will be general in that sense. But it's always useful to kind of have a simpler system that you can kind of use to develop intuition. And so I'll be coming back often to the case of a two-dimensional system, which we can represent nicely on a block sphere. So nice to use a 2D system to get intuition. And sometimes I will use the terminology qubit when I talk about a two-level system. So this just comes from the quantum information language. A qubit stands for quantum bit. So it's the quantum mechanical generalization of a two-level binary system. Okay, where bit is binary, digit. Oh, you're all young, you know what a bit is. Oh, okay. And so, okay, if we take a pure state, a two-dimensional pure state, we can always parameterize it as follows. So let's say I'm considering a spin system, a spin half system that has spin up or spin down. I can always write it as cosine theta on 2 spin up plus a phase, e to the I phi, sine theta on 2 spin down. And actually, Wikipedia has this definition wrong. So if any of you have an account, I encourage you to go and update it because, I mean, and you can first convince yourself that it's wrong, but they don't have these theta on 2s. So maybe that's an exercise. Convince yourself that they're wrong, and then one of you can update it. Okay, and so this state, it's got two free parameters, theta and phi, and it can be parameterized on the surface of a sphere. So let me draw the sphere. Oh, and actually, so you guys are going to be drawing these a lot. So I wanted to have like a short tutorial on how to draw it because it's not as easy as it seems. So everybody get a piece of paper and a pen. So, I mean, there are some key things like one of them is you don't want this axis to be too far out because then it gets in the way of lines that you draw that correspond to the state. So this is, you can draw the sphere how you like, but I found through experience, this is the nice order to do it in. So first we draw a circle. Yeah. Okay. Then you put in the two axes. I want to see people doing this. Come on. Because you're going to be drawing these, and like I've seen some, they're not pretty, right? Like, okay. And then you put in the circle corresponding to the equator. And then like you want to get this axis, like the x-axis, somewhere here, because later you'll be like drawing a state in here and you don't want it to like get in the way of that axis. So in your free time, you should practice drawing these. And I mean, like, I'm serious. So many times when you're having discussions with researchers or your collaborators or something, and you're trying to convey something, and they just want to know what does it look like on the block sphere. Well, then you have to draw the block sphere quickly and on the board and show what happens. So you want to get good at it. Okay, so we have the sphere. It has axes. So typically, that's the z-axis, the y-axis, and the x-axis. And we can label states on this axis So usually the state corresponding to here is the, oh, maybe we can use spin up and down. And then we can label the other points on the sphere, which I will call this plus and this minus, where and I will call this plus I and this minus I. Okay, so some things to note. On the block sphere, states that are opposite each other are orthogonal. So in Euclidean space, orthogonal things are like this. But on the block sphere, orthogonal states are opposite each other. What else? Okay, I will say more things after we talk about mixed states, but for now, we'll stick to that. Okay, so another thing that becomes really useful is that, oh, okay, sorry. Yeah, the other thing I want to say is that these states, they're all eigenstates of the Pauli matrices. So these two states are eigenstates of the sigma z operator. These are eigenstates of the sigma y operator, and these are eigenstates of the sigma x operator. And so one thing, as we know, that we do to states is we evolve them according to unitary evolution. And on the block sphere, the unitary evolution is nothing but rotation. So we can parametrize different rotations, like around the x-axis is just a unitary operator. Like that. And you can write analogous ones for around the z-axis and around the y-axis in terms of the Pauli operators. You can also have a more general one. So you can have an rotation about the vector n, which is going to be some unit vector in the block sphere. And it'll be given in terms of this dot product of the unit vector and the vector that contains all of the Pauli matrices. So just to like test you guys. Let's say if I start off with a state that's here, the plus I state, and I apply this rotation, or this unitary operation, what would I get? Yep. Good. Okay, and so, yeah. I don't know if I want to say much about what will be coming up, but okay, no, let's leave it at that. But yeah, the block sphere will become much more interesting once we start dealing with the generalized axioms. Okay, and then the final thing I wanted to talk about is quantum state tomography. Yes?
This is something that has always confused me about the block sphere, and I'm wondering if you could provide like your thoughts on how to think about the fact that the 2-pi rotation like brings you to negative phase. Is there like a nice way to visualize that, or?
Yeah, I don't know. So
Because that's like that's important.
I mean, I think it might be related to the fact that the orthogonal states are separated by like twice what you would expect in 3D space. So I think if it was in 3D space, 2 pi would take you back to where you are. But here, yeah, no, the other way around. I can't even do it in my head. But I think it's related to the fact that there's like a factor of 2 in what separates orthogonal states. Okay. Maybe let's go to here. Oh, I'll be able to use my sphere. Okay. Yeah, so the reason I want to talk about quantum state tomography is I think it'll give a nice way to get a handle of how we should think about the density operator rho if we can't think about it in terms of physical states. So in order to describe quantum state tomography, I'm just going to switch to the matrix, like vector and matrix representation of kets and operators, because I think it'll make it a bit more intuitive. So I'm going to define the kets. Up is going to be a two-dimensional vector like this, and down is a two-dimensional vector like that. And I'll just remind you of what the Pauli matrices are. So this one it's not strictly a Pauli matrix, it's the identity. And then I've just relabeled them as 1, 2, and 3, but they correspond to the X, Y, and Z Pauli matrices. And so these 4 matrices, they form a basis for a two-dimensional system. So I can always decompose the density matrix as a sum over all of these matrices. And I mean, you can invert this, and you can then see that these numbers A are just given by the trace of the product of the Pauli matrices with the density operator. So you can check this for yourself. You can just take this expression for the density operator, put it back in here, and compute the trace, and you'll get back your expressions for these coefficients. Okay, so what this means is that if somebody gives me let's say someone's preparing a quantum state and I don't know what that state is, physically, they prepare this state and they give it to me. Is there a way that I can know what the density matrix is corresponding to that state? Well, even for the states that we were dealing with, the ideal states, if you don't know anything about the system, there's actually no measurement that you can make on that system to tell you what that state is. No single measurement. But if the person who's preparing that state can guarantee you that they can prepare that same copy over and over and over again, they can send you copies of that state. And you can measure that state in different bases. So you can first measure in the sigma x basis, and then you'll get outcome plus or minus, and you keep repeating this measurement on freshly prepared copies of the state. After some time, you'll get something that corresponds to the expectation value of the sigma x operator, which would be one of these. Then you switch your measurement basis. You start measuring the sigma z basis or sigma y basis and keep repeating many measurements until you build up enough statistics to get the expectation value of that. And then you do it for the third basis. And, oh, I forgot to say A0 is equal to 1. So you only need to do 3 measurements, 3 expectation values, which you need many measurements to make. And from those statistics, you then plug that into your expression for the density operator. Yes?
If you start out with a given quantum state, how does one construct many copies of that state?
Well, you have to make sure that the preparation procedure follows exactly the same recipe over and over again. So you have some sort of, maybe, what's a good example? I have some sort of like oven. Well, oven's not really good because it's kind of random. You need to somehow guarantee that you're doing exactly the same thing over and over again. So, okay, one example is this down conversion that I was telling you about. So I could have this 2-mode squeeze state coming out. I could have a detector in one mode, and when that detector goes click, I know I've prepared a single photon in that other mode, and then that state, well, that system can be sent to someone else. And if I repeat this procedure over and over again, identically, I have reason to believe that I'll be preparing exactly the same thing every time.
But if you made a quantum state, you can't make the exact same copy of that quantum state, right?
You can always, yeah, okay. So if somebody gives you an unknown state, you can't do anything to copy that unknown state. But I can make, let's say, a state that I know what it is, and I can do that like over and over again. And then I can give you that state as a messenger, and now you, the messenger, has an unknown state that can like give it to somebody else who wants to measure it. And so then the process of me making a known state, secretly giving it to a messenger, would be then the process of preparing an unknown state over and over again. Does that make sense? Yeah. Which again now like is a statement about things that agents are doing and knowledge that the agents have about objects, rather than statements about the physical object. Because all I'm doing is giving it to someone and not telling them what it is.
Right, so at least one guy knows.
Well, I mean, not really. So I could be making, let's say that procedure I described about preparing a single photon. So I can know that that photon that comes out is horizontally polarized. And then I can put a wave plate, like So a wave plate is an optical element that changes the polarization of the state. And I can just kind of like spin it, right? And like wait until it stops. And I don't know how it stopped. And like I don't know what polarization it is. But now I can, every time I press play and get a photon to come out and then it goes through the wave plate, it'll be preparing exactly the same state over and over again, but I just won't know what it is. So it doesn't really need an agent knowing what it is in the first place. But in principle, like, you know, I don't know, God or something knows what that state is. Okay, I like don't take that last thing back. I have no idea about what any entity knows. Okay, so let's say we went through exactly that procedure, right? And now I can make these. So I'm making a two-level system that is, rather than being a spin system, it's some sort of polarization system. So it's got horizontal and vertical polarizations. Now I can measure in the three different axes corresponding to the Pauli operators just by like putting in different like polarizing beam splitters and like photon counting and so on. So there's a way to construct these measurements and then build up the statistics. And then I will get some statistics. And so let's look at an example. Let's say when I measure in the sigma x basis, and I build up statistics, so I have like plus x, minus x, and over time I get something that's, you know, 50-50, the same. So I get, so probability of getting plus to plus 1 is 0.5. And then I measure in the sigma y basis. And I also get 0.5, 0.5. And then I measure in the sigma z basis. And I get 1 and 0. So maybe I'll draw these as well. Okay, so I've made multiple copies of the same state. I measured each one in the different bases, and I got these statistics. So from that, I would plug it back into this expression for the density operator. And what would I get? Okay, so that's kind of mean to like ask you to figure that out. And there's a easier way of doing it than, I mean, okay, if you've got you got Mathematica, then it's pretty easy to plug those numbers in. But there's a pretty easy way to figure out how to draw this on the block sphere. So these expectation values of the Pauli operators, they correspond to projections of the three axes. So if this is a unit sphere from 0 to 1, if you calculate the expectation value, you'll know the projection onto the sphere. So the expectation value of sigma x here, well, it would be probability of getting that outcome times its eigenvalue plus the probability of getting the other outcome times the other eigenvalue. Well, that gives you 0. So the projection onto the x-axis is 0. If you go through the same process, the projection onto the sigma y-axis is 0. And the projection onto the sigma z-axis is 1. So if we look at this state, look at the block sphere, and we've got X, Y, and Z, then we know that those statistics correspond to this preparation corresponding to the spin-up state. So when in operational quantum theory, when we think about the density matrix, the way that we should think about it is it's the mathematical object that corresponds to preparing multiple copies of the same physical state and doing quantum state tomography and then plugging all that into like that expression there. And that's the only way that you can think about it. It's, yeah.
What's tomography mean?
Yeah, good question. Yeah, so you know, like CT, like when you go for a brain scan, and so what they do there is they measure two-dimensional slices of your brain, and from that reconstruct a three-dimensional image. And so here, what you're doing is measuring cross sections of the block sphere, essentially, or cross sections of the state, and then reconstructing the three-dimensional state. And so you can actually do this for higher dimensional systems or for any dimensional system. You don't have to be restricted to just two-dimensional systems. So for a three-level system or a qubit, you get a set of 8 3x3 matrices, which are called Gell-Mann matrices, and they also form a basis for the three-dimensional system. And so there you would need to measure expectation values of those 3, and then you can reconstruct the state. So in practice, it gets experimentally more challenging the larger dimensional your system is, but in principle, you can do it. Yeah, so I mean, it kind of seems convoluted thinking about the density operator in that way, but it's the way that ultimately you should think about it when you're thinking about operational quantum theory. It's just to do with things you can do in the lab and statistics that you get. Okay, so that's all I wanted to do. I know the ideal postulates weren't particularly exciting because they are very closely related to everything that you've seen so far, but hopefully tomorrow, once we start looking at the realistic postulates, they're going to be a little bit more interesting. And hopefully I'll have a nice Mathematica demo for you guys to show you how the states on the block sphere evolve under realistic transformations. Are there any questions? Okay, well, let's go to lunch then.